Good morning, everyone. I'm pleased to present our project titled Machine Learning for PCOS Risk Screening. Our project work focuses on developing a clinically aligned, interpretable, and accessible prediction framework that supports early PCOS detection using low-cost, self-reportable indicators. Throughout this presentation, we will walk you through our dataset modeling strategy, explainability framework, and key clinical insights. Let me begin with why this problem matters. PCOS remains one of the most underdiagnosed conditions in women's health despite affecting nearly 1 in 10 women. The diagnostic pathway depends heavily on access to hormonal assays and ultrasound examinations which are not uniformly available. Compounding this, the disorder presents with highly variable symptoms which makes early recognition difficult. What this means is that many women experience significant delays in receiving care. This motivated us to explore whether machine learning could help flag individuals at risk before they undergo expensive investigations. To address this challenge, we started by examining a clinically rich dataset. When we examine PCOS diagnostically, we see four consistent barriers. Symptoms overlap with many other conditions, leading to ambiguity. Confirmatory testing requires infrastructure that is often limited to tertiary centers. Many patients lack access to specialists, leading to delayed or missed diagnosis. In essence, the clinical pathway is reactive rather than proactive. This creates a gap where data-driven tools can support preliminary screening, and this is the gap our model is designed to fill. With this background, I will now hand it over to Swami, who will walk you through the dataset and modeling framework.
Hi, this is Shoni. I will discuss about the dataset as well as the architecture of our model. Our dataset consists of 541 patient sample collected from 10 hospitals across Kerala, making it one of the prominent datasets available for PCOS research in online domain. We began with all 41 features spanning demography, clinical symptoms, ministerial characteristics, hormonal levels, as well as the ultrasound findings. After performing systematic correlation analysis, we removed 3 highly correlated variables resulting in 38 validated features. This gave us a well-structured dataset that effectively captured the multi-system nature of PCOS. Before modeling, we needed to ensure the dataset was analytically robust. These slides summarize the quality assurance steps that prepare the dataset for modeling. We handled missing hormonal ultrasound values through median imputations, ensuring numerical stability. Binary encoding was standardized, and continuous variables were min-max scaled to align different measurement ranges. Because of PCOS class in slightly underrepresented, we applied borderlines mode to sharpen the decision boundary for classical model. We also mitigated outliers, especially AMH and LHFSH, which are traditionally skewed biomarkers. Together, these steps produce a clean, balanced dataset ready for machine learning. However, not all clinically measured variables are suitable for real-world screening. That motivated our next step. In the context of PCOS screening, our aim was to prioritize accessibility. Out of the 38 validated features, we selected only 10 that our individual can reliably self-report without laboratory or imaging support. These are those 10 symptoms which actually they normally inform their doctors for the initial diagnosis. This includes easily observable clinical symptoms such as hair growth, acne, cycle irregularity, darkening of skin, and some continuous variables like age, weight, cycle length. This design choice ensures that our final model can operate in low resource or community level environments while still preserving clinically meaningful science. With feature finalized, let's look at our learning architecture. Our predictive framework uses a two-level stacking ensemble. At level 1, we deployed 4 heterogeneous models: logistic regression for linear discrimination, random forest for partition-based learning, XGBoost for gradient-boosted optimization, and a new neural network designed to capture smooth nonlinearities. Each model generates out-of-fold prediction which serve as unbiased meta features. At level 2, a gradient boosting classifier learns how to optimally weight these signals. This architecture enables the system to integrate complementary decisions patterns, improving robustness and applicability beyond what any single model can achieve. Let's now interpret how these models behave inside the ensemble. Using SAP, we evaluated how each base model influences with final output. What we observe is that logistic regression provides the strongest stabilizing effect, acting almost like the backbone of the ensemble. The neural network and random forest contribute subtle nonlinear interactions, complementing the linear model. XGBoost provides final adjustment, refining borderline cases. This layered contribution structure shows that the ensemble is not dominated by a single model. It benefits from diversity, which is critical for clinical reliability. Now let's compare model performance to see how this translates in practice. Here we evaluate the uplift produced by stacking. The gradient boosting meta-learner reaches an AUC of 97%, suppressing all individual models. We also see notable gains in accuracy and F1 score, indicating improvement in both precision and recall. Cross-validation scores remain consistent, confirming stable generalization. What this tells us is that the ensemble succeeds in extracting complementary strength from the base models, achieving a performance level that is clinically actionable. I will now hand the presentation back to Anisha, who will discuss insight, limitations, and future directions.
This study demonstrates that even with only 10 self-reportable features, we can achieve strong predictive performances. The model captures multidimensional patterns that reflect genuine clinical signals such as menstrual irregularity, androgenic symptoms, and metabolic trends. Furthermore, the stacking framework ensures that no single modeling assumption drives the predictions, increasing reliability. Overall, this confirms that machine learning can play a meaningful role in low-cost PCOS risk stratification. Next, let me outline the limitations that define the scope of this work. While our results are promising, there are several practical limitations. The dataset size, though valuable, remains modest for a condition as heterogeneous as PCOS. Being region-specific, it may not fully capture ethnic or lifestyle diversity. Some clinical attributes contain missing values or depend on subjective reporting. Additionally, although stacking improved performance, deep learning components would benefit from larger datasets. These factors highlight the importance of cautious interpretation when generalizing to new populations. These limitations inform the roadmap for the future development. Future work will focus on scaling both the dataset and the application. We aim to collect multi-regional clinical data to strengthen generalizability. We also plan to develop a lightweight mobile-based inference engine that can run offline, enabling screening in low infrastructure settings. A clinician-facing SAP interface will aid transparency, while advanced architectures such as tabular transformers may further enhance performance. Finally, conducting prospective clinical validation will be essential before real-world deployment. I will now conclude the presentation. To summarize, this project shows that accessible, interpretable machine learning can substantially support early PCOS screening using only simple, self-reportable indicators. The stacking ensemble achieves strong predictive accuracy while maintaining clinical transparency, bridging the gap between AI research and real-world healthcare needs. Our work lays the foundation for scalable, equitable women's health screening powered by responsible AI techniques. Thank you.